Let me start with a question for you. When you think about pineapples, you're probably thinking about a snack, uh, not orthopedic surgery.
Not at all. Yeah.
But according to this 2026 study we're looking at today, the spiky leaves we all just throw out might be the future of it.
It sounds a little absurd at first, doesn't it? But when you actually dig into the data on pineapple leaf fiber, or PALF as they call it starts to look like serious material science.
We are doing a deep dive into the mechanical properties of these fibers, specifically for biomedical use. And the big takeaway for me is that we're not just, grinding up leaves.
Not even close. We're talking about a material that's somewhere between 70 and 80% cellulose.
Yeah.
It has this incredibly high specific strength.
And that's the key metric, right? Specific strength.
It is. It's strong, but it's also really, really light. Only about 1.5 grams per cubic centimeter. The whole study is about taking that raw potential and using it to reinforce polymers for implants.
Okay, but the process here is what really caught my eye. They aren't just using the raw leaves. They give them this 5% sodium hydroxide bath.
Yeah, the alkali treatment.
And it seems absolutely vital for getting the fibers to bond with the resin.
Oh, it's non-negotiable. You have to strip away the impurities, the lignin, that waxy outer layer. If you don't, you just get terrible adhesion.
So it roughens up the surface.
Exactly. It basically creates these microscopic locking points. Think of it like a natural Velcro between the fiber and the epoxy it's set in.
And that's what gets us into this Goldilocks zone for replacing bone. I think this is the most important part for you to understand. Why do we even need this when we have titanium?
It all comes down to something called stress shielding.
Right.
Metal is often just too strong, too stiff. If the implant is so much stiffer than the bone, it takes all the load and the bone around it. It gets no stimulation.
So it starts to weaken. It's not doing its job anymore.
Precisely. It can actually dissolve over time. So you need a material that sort of matches human cortical bone, which has a tensile strength of, say, 50 to 150 megapascals.
And looking at the charts in the study, this pineapple composite, it lands right in that window.
It does. And it's a really clear linear progression. At 5% fiber, the strength was only 45 MPa.
Okay.
But when they ramped it up to 25% fiber, it jumped to 78 MPa.
So it's strong enough to support the bone, but flexible enough to make the bone keep working? And the bending strength, the flexural strength, that was even higher, right?
Yeah, that peaked at about 112 MPa. But like you said, strength is one thing. You can't have an implant that shatters on impact.
That's where this bridging idea comes in.
Exactly. They looked at the fractures under a scanning electron microscope. And when a microcrack forms, the fibers literally stretch across the gap.
They stop the crack from spreading.
They stop it in its tracks. The material with 25% fiber could absorb almost double the impact energy. It's tough, not just strong.
I want to pivot to the friction and wear, the tribology. Because if you're putting this in a joint, it's going to rub against things. And you would think that adding rough, natural fibers would increase friction.
That was the really counterintuitive finding here. You'd expect it to get worse.
Yeah, much worse than a smooth polymer.
But they found the opposite. Adding more fiber actually reduced the friction coefficient down to 0.51. It was significantly better than just the resin by itself.
So the fibers are actually helping to support the load and resist the micro-cutting forces that chew up the surface?
It seems so, which makes it durable enough for sliding parts, things like knee or hip supports. It opens up a huge door for prosthetics.
It's a really compelling case. You've got a material that mimics bone, prevents stress shielding.
And it's made from an agricultural byproduct.
Yeah.
Stuff that is usually just burned or sent to a landfill.
Plus, it's non-toxic, biodegradable. So you're solving a compatibility issue and a waste management issue at the same time.
You're closing the loop, turning a disposal problem into a potential biomedical solution.
It just makes you rethink waste, If we can engineer something as common as a pineapple leaf to match human bone mechanics this well, what other agricultural trash are we just ignoring that could be the key to the next generation of life-saving materials?